Here's a puzzle for you. There are dozens of graph neural networks out there, and almost every explainer treats each one as its own separate, complicated model. But here's the thing. Almost all of them are secretly running the exact same recipe under the hood. That recipe even has a name. It's called message passing, and Gilmer and colleagues wrote it down cleanly in 2017. Once you see it, GCN, GAT, GraphSAGE, and the rest stop looking like a confusing zoo of models and start looking like simple variations on a single shared theme. Let's walk through it together. Message passing is really just one loop that every graph network runs. Follow it once, all the way through, and the whole family suddenly clicks into place. First, every node builds a message for each of its neighbors. That message is computed from the node's own features, its neighbor's features, and sometimes the connection between them. Think of it as what this node wants to tell each of its contacts, tailored a little to who's on the other end. Then, each node collects all the messages arriving from its neighbors and combines them into one summary. Crucially, the combining rule ignores order, using something like a sum, a mean, or a max, so it doesn't matter which neighbor happened to speak first. A node's neighbors form a set, not a list, and the math has to respect that. Next, the node updates its own hidden state using that aggregated summary, often through a small neural network. It folds in what it just heard from the neighborhood, arriving at a fresh representation of itself for this round. Finally, you repeat the whole loop for several rounds. Each round pushes information one step further out, so after a handful of rounds, every node effectively knows about its wider neighborhood, not just its immediate contacts. So what does this replace? Here's the shift, side by side. The old way was to hand-design features from the graph yourself. You'd manually count triangles, measure degrees, engineer whatever structural signals you could think of. It's rigid, laborious, and it only captures the patterns you already knew to look for. Message passing learns to propagate information over the graph instead. Rather than handcrafting what matters, the network discovers useful patterns on its own by sending, aggregating, and updating, round after round, tuned directly to whatever task you're training on. The features become learned, not guessed. So what should stick? 3 ideas carry the whole framework. First, the recipe itself. Message, then aggregate, then update every single round. That triple is the engine, and it runs the same way whether you're on a molecule, a social graph, or a citation network. Change the 3 functions and you change the model, but the loop never moves. Second, aggregation ignores order. A node's neighbors have no natural ranking, so the combining step uses a sum, mean, or max, where reordering the inputs never changes the answer. That property is exactly what makes it work on graphs. Third, it unifies the whole field. GCN, GAT, GraphSAGE, and most graph networks are just different choices of those 3 functions, nothing more. And thinking this way even explains their limits, like why stacking too many rounds smears every node's features into the same mush, a problem people call oversmoothing. Alright, let's lock in the takeaways worth keeping. Message passing, formalized by Gilmer and colleagues in 2017, is the general recipe almost every graph neural network follows. Every layer runs 3 steps. Each node builds messages for its neighbors, aggregates the messages it receives, and updates its own state. Aggregation must ignore order, so it uses a sum, mean, or max, and repeating the loop for several rounds spreads information across the graph. GCN, GAT, and GraphSAGE are just different choices of the message, aggregate, and update functions, which is a genuinely liberating thing to realize. If seeing the pattern behind the models is the good stuff for you, Standarity.com is absolutely packed with it. See you over there.